Hi folks, we're going to take a look at 5D from page 179. So they give us this function here, which is just the cube root of x squared minus 1. And they ask us to find the critical points, determine if there's any local maxima and minima, and determine if the tangent at these points is parallel, they say, to the horizontal axis, so meaning to the x-axis. In other words, is the tangent horizontal at those points. Okay, so first thing we'll do, of course, is to calculate the derivative. So here we just have 1/3 x squared minus 1 to the negative 2/3 times the derivative of x squared minus 1, so 2x. And here, since I have to work with this, let me simplify here. So the only thing that stays in the numerator will be the 2x. Okay, and in the denominator we have the 3x squared minus 1 to the 2/3. Okay, so in order to find the critical points, we have to determine when f prime at x is equal to 0. And here, since we have a fraction, the numerator needs to be equal to 0. So here, x equals 0 is what satisfies that condition. And in order for the derivative to not exist, well, in this case here, again, because we've got this expression with just powers of x, we just have to check when the denominator is equal to 0. So when x squared minus 1 is equal to 0, in other words, when x is equal to plus or minus 1. So these are going to be our critical points. Now notice here, they're not just critical numbers, they're actual critical points. Because if I go back to the original function, this function is defined everywhere. Okay, 1/3 does not have the same restrictions as exponent 1/2 does. So these, in fact, are all critical points. Okay, so here, let's put in 0, -1, and 1. So of course, I'll use the first derivative test to see if there's any local extrema. So here, one thing I notice about my derivative, again, something to really look for, is because of this 2 in the numerator of the fraction, that means I'm squaring this expression, x squared minus 1. So this is always going to be positive, and I'm just multiplying it by 3. So the denominator is always positive. So the only thing I need to look at is the sign of the numerator, since that's always going to be positive. Okay, so here, if I put, -2, the numerator is going to be negative, meaning the whole thing is going to be negative. If I put in -0.5, numerator is going to be negative, the whole thing is going to be negative. If x is 0.5, numerator is going to be positive, so whole thing positive. If I put x equals 2, numerator positive, the whole thing is positive. Okay, so I notice here that this is the only value at which I have a local extremum, and because I'm going from decreasing to increasing, it's going to be a local min. And at -1 and +1, I do not have a local extremum. Okay, but let's answer the question about the tangents here. Okay, so in this case here we have at 0, well, we see that the derivative is equal to 0. Okay, meaning that we are going to have a horizontal tangent. So horizontal tangent at x equals 0. But here, since at 1 and -1, the derivative does not exist, we do not. Okay, but not at x equals plus or minus 1. Okay, so now the question is what kind of derivative do we have? So we know it doesn't exist, but do we have a cusp there? Do we have just a point of inflection that has a vertical tangent at that point? So if we wanted to investigate further, we'd have to, use the second derivative here, but I'll just show you quickly here what the function looks like if you graph it. Okay, so here, if you want to see something a little freaky there, ooh, wow, look at that. Anyways, but if we look at the graph here, we notice that at 0, so we have our minimum, and then at -1 and 1, we have derivatives that don't exist, but we indeed have points of inflection there. So if you found the second derivative, you should be able to determine that we have points of inflection there. Okay, so that's it for this one.